Good morning, everybody. Just like last time I was here, I started out my talk with some music from a native New Orleanian, and this guy's name is Mystical. Who's heard of Mystical before? I guess I'm the only one that hasn't. Okay. So anyway, that's he's from here, and the CD cover is pretty cool, I think. So if anybody recognizes that, there was this design company back in the 90s and early 2000s that did all these rap covers called Pen and Pixel Graphics. And they ended up being the in-house design firm for No Limit Records. So you can see like maybe this one you had in your collection, or this one, or this one. You can kind of see they have a pretty distinct style. It's pretty easy to recognize. They were on top of the world back in the day. Unfortunately, I don't think they're doing as well right now. This is their current webpage. I know. Sorry. All right, anyway, I'm not here to talk about Pen and Pixel. I'm here to talk about Phoenix Project, but let me introduce myself first. That's me, Todd Resudek. All right. Find me online, super simple. I'm a staff engineer at Jackpocket, and as Alex mentioned, I'm a member of the Hex Core team. All right, so a little bit about me. I grew up in Wisconsin. I was waiting for the applause. Okay, nobody from Wisconsin. I meant if you're from Wisconsin. Amy, come on. All right. Moved to Los Angeles. Somebody's here from LA. Come on. Albert, come on. All right. Do we understand what we're supposed to do now for the next one? Okay. If you're from this city, or you live there now, clap, okay? Ready? All right, New York City. There we go. Moved to New York City, and now I live in Colorado. All right, so this is a pretty serious talk, but before we get started, I actually do want to take a little time out to just mention a man that we lost recently in our community, and without him, a lot of these talks wouldn't be possible. Steve Wilhite. He's the inventor of the GIF, or GIF as he would say. Sorry, Steve. So, pour one out for Steve today. All right, so the talk's called The Phoenix Project, LiveView and the Theory of Constraints. And some of you might recognize the name. It's a reference to this book. I was also told that the Phoenix Project is the name of a project in SETI for the search for intelligent life in the universe by analyzing radio signals. It's not about aliens. You may end up wishing it was about aliens, but it's not. It's a talk mostly about the theory of constraints. And the theory of constraints was originally introduced in this book called The Goal. And I'll talk a little bit more about how that applies to software development lifecycle. But I just wanted to call out the author, Dr. Eliyahu Goldratt. Heavy drip game, this guy. So he puts himself on the cover of his book. It's kind of crazy, but if you look as good as him, you would too, probably. I also make reference to a couple other books. This one, Accelerate, by Nicole Forsgren, and Team Topologies. All right, so the talk is about a real project. I'm just going to call it the Phoenix Project. And by the way, we're 25 slides in. I haven't showed any code yet. And we have about 70 more slides to go. And exactly one of them has code. So pick your number. Try to guess which slide is going to have the code in it. And I'll let you know when we get there. You can find out if you're right. So about the Phoenix Project. So the Phoenix Project was this admin website for a company out called Sports Unlimited, Inc. It was greenfield work. Didn't have any existing code, didn't have an existing team. And our UX and our UI were provided by a designer. The main goals were ease of navigation, speed of interaction, as well as getting real-time updates of data. So when we started out, or we're kind of planning for the Phoenix Project, we started looking at our previous projects. And so I'll call that Project X. Project X isn't really one project. It's kind of a culmination of a lot of projects that the people involved brought in from their past. So it's based on experiences that were common in all of those projects. And so Project X, looking at the team composition, usually about 4 to 6 back-end developers, right around the same, 3 to 6 front-end developers. Then you had a product owner, an embedded designer, an embedded SRE, maybe a couple of others. So this is a basic composition of Project X. And so we sort of looked at Project X and started by looking at the flow of work. So the flow is just basically how work moves throughout your system. So you can see in this diagram, we start out with the requirements and sort of work all the way up to the UI work before we deploy. And sometimes what happens in the flow is you get all the way to the UI work and realize, oh, there's something that we needed in the API that we don't have. And so in like lean manufacturing, you would have these and-done handles between each step. And if something's going wrong at your step, you pull the handle or hit the button, whatever. The red light goes off, and everybody sort of focuses on that. We don't really have that in software. So what would happen is, we'd go all the way to the UI phase. We'd find this problem, say, oh, I need this field to be this type, or I need this extra field in the API so that I can show it in the UI later on, or I need you to calculate some value, et cetera, et cetera. And so we would have to go all the way there and then create this new unplanned work, push it all the way back to the beginning of the flow process, say, here's the new requirement, and kind of put everything on pause until it came back through the system. And so flow, the reason why we started with flow is it's probably the most observable way to determine how well or how poorly your system is working. You get a really good kind of bird's eye view of kind of where the hiccups are in your system, what's moving slowly, what's moving faster. And ideally, your flow would be a very consistent, predictable cadence. So over time, you would be able to basically gauge how fast something should move through the system. It won't be fits and starts. And so when we're looking at the flow, then you kind of naturally go into the theory of constraints. So the theory of constraints is a theory, it's a theory in the management paradigm that views any manageable system as being limited in achieving more of its goals by a small number of constraints. There's always at least one constraint, and the theory of constraint uses a focusing process to identify the constraint and restructure the rest of the organization around it. Okay, so this is kind of a heavy concept. Like that whole book, the goal is the theory of constraints. And so this is just kind of a short version of it. But so in any system, like I said, there's one part that's the slowest. And you can think of that usually as being the constraint. The process involves identifying that constraint. You could call it a bottleneck. And then making changes in the system to increase the throughput there. Now, after you've done that, something else is the constraint. So in a factory, the easy way to identify this in a factory is to basically look at all the different workstations and see where product is piling up. So if you're in like a car factory and you've got sub-assemblies of motors or something that go into frames at the next station, and now you've got 10 motors stacked up here, it's a pretty good visual example of where your constraint is. So obviously your constraint is right after that motor or somewhere after that motor in the system. It's a little bit harder to do in the software development lifecycle because we're not looking at motors, but there are definitely ways to do it. So for visual learners, it's kind of a visualization of how that works. So you can see like the intake step, and then step 1 has a lot more capacity. Step 2 is our bottleneck. And so, when you look at the system, it's important to know that nothing's ever going to move faster than the bottleneck. So even though you've got great capacity in step 1 and step 3, the system is never going to produce anything faster than what step 2 can handle. So to deal with the theory of constraints, you've got like this 5-step plan. So the first thing is you've got to identify what the constraint is. So step 2 in this case, or where the motors are backing up, et cetera. Next is to exploit the constraint. So eliminate everything in there that doesn't add value. So if there's things that you're doing in that step that aren't adding value to the customer, get rid of it. Then you subordinate everything else. So this one is really hard to explain to managers, but essentially, there's no use in running step 1 or step 3 at full capacity if step 2 is going to be the thing that's controlling your output. And so in lean manufacturing, they would actually say, just leave those stations idle. Like, they should be producing as much as as step 2 can handle and no more. And if that means that the people there are working half days, then so be it. It's actually better for the company that they do that than for them to pile up a bunch of assets. So subordinate everything else, and then the next step is to elevate the constraint. So devote resources. Figure out what can we do in this case, step 2, what can we do at that constraint to make it move faster? So it could be, breaking apart the work that's done in step 2. It could be putting more resources in it. So in a manufacturing facility, it might be like, let's add another machine. In software development, it might be, something else, add a tool to our system, lean on a SaaS product or something instead of building it ourselves, whatever the case is. And then once you've done that, you go back to step 1, figure out where your new constraint is. All right, so how does this apply to Project X? So we've talked a lot about manufacturing, but how would this apply to the software development lifecycle? So when we looked at Project X, for us, the constraint we found was this handoff between the back-end team and the front-end team. And so we started looking, are there tasks in the handoff that maybe aren't necessary or aren't providing value? Or can we work in smaller batch sizes? What can we do basically to alleviate that constraint? So we identified our constraint. It's this handoff between back-end and front-end. Let's remove unnecessary tasks from the handoff process. Is there a ceremony that's involved that we could get rid of? Some meeting that we could get rid of? And while we do that, if the handoff is after the back-end work is done, can we, instead of just having the back-end developers be idle, are there tech debt tickets or something that they can work on? Instead, just so they're not working half days, but they're doing things that aren't going to hit that same constraint later on. Do we bring over more resources? Is there somebody, some role that we can add in that exchange that's going to make this faster? But what if? So had us thinking, what if there wasn't a handoff at all? And that's where this book comes in. All right, 42 slides in, we've introduced LiveView. How's that? All right, so now let's look at the flow of the system again. So now we're using LiveView, right? We go from requirements to back-end work to UI work, and that's it. The flow is quite different in that. So if we find this issue in the UI work like we found before, instead of going all the way back to the beginning, we maybe go back to the previous stage, or it might be the fact that it might be something that the person that found the problem in the UI can also fix themselves in the back end, or at least it's in the same group. And since the issue is kind of fresh in their mind, that bit of code is fresh in their mind, the context switching is minimalized, so it actually might even be faster for them to fix that than it would be in the old type of flow. So I'll get back to this in a minute, but let's talk about implementation. So how would we do that? If we've never done that before, how would we build this team to work in this type of flow? And whenever you're doing that, whenever you're proposing any kind of a new architecture, you should be considering Conway's law. It's not that Conway. So when you hear Conway, you probably think of this guy, John Horton Conway, PhD of Sydney Sussex College, Cambridge. Nobody from Cambridge? Okay. But you probably know him from Conway's Game of Life. It's like a fun little programming project. And he was a specialist in the CGT, combinatorial game theory. So that's John Horton Conway. But Conway's law is actually named after this guy, Melvin Conway, PhD from Case Western Reserve. Somebody just applaud, pretend like they went there. Thanks. All right, go Spartans. And other than Conway's Law, he's most famous for working on the MUMPS spec and publishing the MUMPS manual. MUMPS? We got a MUMPS guy?
I used to do MUMPS.
See? Okay. MUMPS is anybody else worked in MUMPS before? Very esoteric language that's mostly used in the medical system, if you worked at the VA, or occasionally at financial products. So it actually stands for the Massachusetts General Hospital Utility Multi-Programming System, MUMPS. It's a very forced acronym, but it's pretty cool. I got time. I've got a little aside on this. I met a guy once who did MUMPS, and he's like, yeah, there's like 12 of us that still specialize in MUMPS, and so when the VA needs somebody, they don't ask you how much you get paid, you tell them how much you get paid. So it might be good to get into. All right, so sorry, let's get back to it. Conway's Law. This is huge. So any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. Learn that. This is an easier way to put it. So if you have 4 teams working on a compiler, you're going to get a 4-pass compiler. So essentially, your architecture is going to end up being set up the way your org structure is set up, and who's talking to whom. And so if you're not being very deliberate about this as an engineering organization, these decisions are being made by other people. So it could be a high-level manager. Heaven forbid, it could be your HR team that's designing the teams. But somebody's essentially designing your architecture for you when they're building these teams out. So just an example of Conway's Law. So we look at 4 applications here. We've got 4 front-end teams, 4 back-end teams, but they have a shared DBA and a shared SRE. And Conway's Law would say, the emergent architecture would be a decoupled front-end, back-end, but a monolithic shared database and a shared infrastructure. So you would see, what you would expect to see out of this would be one database that all 4 applications are kind of using, and one kind of deployment strategy, or maybe one Kubernetes cluster, or whatever it is, because there's one person that's trying to do all 4 of those jobs at the same time. So that's when this bad boy comes in, the inverse Conway maneuver. Anybody ever heard of this one before? Where's Dave? Okay, there he is. All right. Okay, so the inverse Conway maneuver recommends evolving your team and organizational structure to promote your desired architecture. So if you think of what the architecture is that you want to end up with, what you should be doing today is building your team to reflect that. Your team structure is your first draft of your architecture. So if we do something like this, the inverse Conway maneuver, and we add DB resources and add SRE resources, we should expect the system to be far more decoupled than the previous one. So for the Phoenix project, this was our proposed team structure. Backend, DB, SRE, and that's it. We removed the independent front-end team. So back-end team and the front-end team were all the same people. Won't that just put more work on the back-end team? Well, maybe, but not really. Let me explain. So communication structures are the reason. The team size matters. A larger team size requires more communication structures, and that's overhead. This follows Brooks' Law. So Brooks' Law is an observation about software project management, according to which adding manpower to a late software project makes it later. So some of you may have read or heard of the book, The Mythical Man Month, and it basically asserts that under certain conditions, adding an additional person actually makes the project take more time versus less time. And the reason for that, well, part of the reason for that is this combinatorial explosion. So a combinatorial explosion is a rapid growth of the complexity of a problem due to how many combinatorics of the problem is affected by the input constraints and the bounds of the problem. All right, this is what it looks like. So you've got linear growth. This is ideal. you've got exponential growth, which we all know is like significantly worse, and then literally this is what combinatorial explosion looks like. So yeah, it gets out of hand very, very fast. And so if you apply that to like Brooks' law, you look at the additional overhead of these communication structures going from a team of 5 to a team of 10. So a 5-member team has 10 total connections, and an 8-person team, sorry, this is an 8-person team, has 28 connections. So you add 3 people, now you've just about tripled the number of communications that you have to assess. And like you can think of these black dots as people, but you can also think of these as nodes in your Erlang application as well. And so you can see there's a lot of noise that's created as you add additional resources. There's a lot of overhead just having them talk to each other every day. So that's kind of why adding an additional person, that's one of the reasons why adding additional people to a team doesn't necessarily make it faster. Another one is Dunbar's number. It's kind of, let me explain what it is. So it's a suggested cognitive limit to the number of people with whom we can maintain social relationships. So the strongest form happens in an individual, like a team that's working closely together. Usually that group size is around 5 to 10 people. What they've studied in software is that number is around 8 people, and this follows the, if anybody's ever heard of the 2-pizza rule at Amazon, is like no team should be bigger than can be fed by 2 pizzas. So that kind of follows that. So there's an ideal number of people where if you grow outside of that, it creates more problems. So teams working as a cohesive unit perform far better than collections of individuals. So you think about it, you've probably worked on teams where you don't communicate very well, you don't work together, maybe don't get along with your coworkers, and it's just 5 people kind of doing work, the same kind of work at the same time, versus you are on a team where you all really mesh, sort of pick up on what each other are doing, et cetera, and that kind of team, that cohesive team, is going to be a lot more productive. So any growth beyond this Dunbar's number, it sort of imperils the viability of software by the team because the trust is starting to break down. You're getting to a number that's too large where you don't trust the people that you're working with anymore, or you don't have that kind of closeness with them. And so that's kind of where things start to break down. So your team of 5 going to a team of 10 definitely doesn't have that linear growth and productivity because of this. And part of that is just the communication structures. So I think another reason why you can work faster as a smaller team of backend developers has to do with queuing theory. And queuing theory is a mathematical study, basically, of waiting in lines. And the origins of its research were done by Agner Erlang at the Copenhagen Telephone Exchange Company. So it's a name that should probably ring a bell. No pun intended. I really didn't intend it. I just know. Okay. All right, so queuing theory explained in a picture. So you've got incoming traffic, you've got some queue system, and then you've got these service channels where they exit. And so if we think of that as like in a store, you've got like customers coming in, waiting in these queues, and then you've got cashiers at the other end. And so Little's law sort of explains this. It's the long-term average number, L, of customers in a stationary system is equal to the long-term average effective arrival rate, lambda, multiplied by the average time, W, that a customer spends in the system. So that's Little's law. And so you can think of that as think of a small store that just has one register, and then assume everyone that enters the store will buy at least one thing. And if the arrival rate is greater than the exit rate, the queue size eventually approaches infinity. And if you think about this in the software world, it's kind of like your backlog. Eventually it will reach infinity because things go in a lot faster than they come out. So we've applied this to the software development lifecycle. Think of these as like your JIRA tickets. So you've got JIRA tickets coming in. You've got your sprint commitment is the queue, and then you've got developers on the other end are your cashiers. That's your bottleneck in the system. And so JIRA tickets arrive faster than they can be completed, and you start to get backed up. Now, if you have a back-end team that's delivering to a front-end team, now you have two queues. So you've got to deal with the bottlenecks at the top queue, and then you've got to pass that on, and bottlenecks at the bottom queue as well. So now you've got two bottlenecks to deal with. And so that's kind of my assertion on why I think having just one team work on everything should be slightly faster than having two teams working on it. In the case of Project X, like this explains where our bottleneck was. So in the Phoenix project, we got rid of that. That bottleneck is gone completely. Another reason is complexity. So we look at Project X, just the overall complexity of those projects. And they have this high cognitive load. So one thing that's important is cognitive load affects all of us. You might think you're like a 10x engineer, but this is something that's biological, and cognitive load will affect you as well. So it's just basically the amount of working memory that you have. Some people do have more, some people have a little bit less, but everybody has a level. And so you've got, basically it's broken down into three parts. You've got this intrinsic load, which is just, how difficult is this subject that I'm working on? How difficult, inherently difficult is this project? And then you've got this germane load, which is the new information that's coming in that you're having to synthesize to work on it. And then you've got extraneous load, which is all the other things that are going on, related or unrelated to that problem. So a complex system is just entirely impossible to reason about. You can't, no person in a complex system could understand how all of it works. So by reducing the complexities in the system, it decreases the overall cognitive load. So we've got, like, this is the anatomy of Project X. I think this is super common. You've got like this Phoenix app, and then you've got this API code. And then on the front-end side, you've got some HTTP client that's dealing with the API, and then you've got this React app or Vue app or whatever it is. And just so much disparate code there that it creates this really high cognitive load in the overall system, and just makes it really hard to reason about. Now, if you look at the anatomy of a LiveView app, got a lot less code. So you basically just have the LiveView code in the Phoenix app. And additionally, like the front-end code is kind of similar to the back-end code. So the context switching is easier. The feedback loops are also smaller, as we explained. Like if you run into something on the front end that needs to be fixed in the back end, you're able to iterate through that, I think, more quickly. When I said the code is similar, who had slide 87? This is our code slide. Hope everybody can read that. So if you had 87, bingo. So the code size is smaller. There's less code. But also, like, if you look at the callbacks or the life cycle of a LiveView process, it looks really similar to gen servers. So you're not doing that context switching of going into a React state machine versus how gen servers work or ETS works or et cetera. The front-end lifecycle looks a lot like the back-end lifecycle. So that makes it a little bit easier. So the callbacks in a LiveView app are these ones, handle call, handle cast, handle info. These are all like lifecycle events that exist in gen servers as well, and they work the same way. So just kind of makes everything easier to understand. So some other advantages that we found would be just easier contract testing and integration testing. Instead of setting up these different proxy servers and stuff, everything's kind of running together. So doing the contract testing between the UI and the back end is simpler. You can do it all in one place, or the integration testing all happens in the same code base. More flexible resources. So everybody on the team can work on all the tickets, essentially. So you've got a UI ticket, you've got an API ticket, you've got data schema ticket, et cetera. Everybody's able to sort of move around better. And we didn't need to hire any JavaScript developers, which, if you're trying to hire anybody right now, it's pretty much impossible. But JavaScript developers especially, it's hard to find. And so that's an advantage as well. We had Elixir developers, and so we were able to kind of use the resources that were already on staff. Now, To be honest, there's some drawbacks. There's definitely some disadvantages of doing this. One is like the pre-built components. So in the JavaScript world, there's a library for everything. So you're like, hey, I need a calendar that, uses the Roman, Julius calendar, et cetera, and, doesn't adhere to leap days, or et cetera, et cetera. And you're like, oh, yeah, I'll just download that one. That's an NPM package. In LiveView, you're generally going to be building everything yourself, which is good or bad, but it does mean it's probably going to be a little bit slower. Lots of breaking changes in LiveView since it's a 0-point release. I know that it's coming up. It's at a very much more stable version now, but when we were working on this, the APIs were changing every 2 to 3 weeks. And so that's, it's a less mature system, so you kind of have to deal with that. All right, so how did it end up? So actually pretty well. So we were able to spin up the team really fast. The product ended up meeting all of our requirements for real-time and interactivity. And with the design, we ended up being able to use reusable LiveView components. And so that helped a lot, and also pulled in Tailwind UI, which were able to help us out a lot on the design side of things, just the overall kind of look and feel of things. All right, that's kind of it. So thanks, everybody.